So in Chapter 15, this is the name of what we're trying to do. Notice that we have differential equations where the coefficient of the second derivative, first derivative, and the variable y are all constants. That's linear. And it's equal to 0, homogeneous. So here's what some of them would look like using the terminology y double prime for the second derivative of y with respect to x, y prime first derivative of y with respect to x, and y, of course, is y as a function of x. We could also have y's as function of t's. We could have q's as function of t's. These all solve the same way. Now, if you remember back to an earlier chapter when we were solving first-order linear equations with constants, we found the integrating factor, and when we found the solution, it had e in it. And so we're thinking maybe the second-order equation might have e's in it. So let's see what would happen if we just guessed a solution like y equals e to some number x, or something times x. And so let's do the derivative and the second derivative, plug all of those into the equation. Now since e to the rx is always going to be positive, we can divide that out. And so this, for a second-order linear equation with constant coefficients, is called the characteristic equation. Now, that's a quadratic equation, so we can solve quadratic equations kind of easily. So we're going to take a look at these three sorts of things and see what would the characteristic equation look like. For the first one, the characteristic equation would look like r squared minus 5r plus 6 equals 0. And so again, notice the characteristic equation for each of these is a quadratic equation. And of course we can solve quadratic equations quite easily. Now let's see what happens when we solve the characteristic equation using the quadratic formula. Remember, in solving the quadratic formula, the thing under the square root, the discriminant, tells us the nature of the solutions. There's three situations that can arise. Either the discriminant is positive, 0, or negative. Now, if the discriminant is positive, we've got two real solutions. If the discriminant is negative, we've got one solution, but it occurs twice. And then we got two complex solutions if the discriminant is negative. Now, I'm going to show you this, and then we'll see how it works. So, for the two solutions, if we have two real solutions, we have ce to the r1x and ce to the r2x. In other words, the two roots are just the exponents on the e. So we have the one solution, which is a combination of the two independent solutions. Now for one solution, where we have multiplicity 2, we have to insert a factor of x. And this is a little stranger. For complex solutions, it's really the same thing. We just take the complex number and use it as the exponent. However, it's common, and I'll show you how this comes about, to use something equivalent to this that is not in complex form. Here is the equivalent that's not in complex form. Now, again, I'll show you later in a different PowerPoint how this happens. But these three things we need to write down in our notes and have handy, because that's how we go about solving the second-order equations that have constant coefficients. Now, I'll show you these examples. In this first one, you notice we take the characteristic equation, solve that, and again, we can solve that on our calculator. We can factor it like we did back in beginning algebra. however we solve it, we get the two roots to the characteristic equation, 2 and 3. So we write the answer from what I had on the previous screen. C1e to the 2x and C2e to the 3x. Here's another one that illustrates the other types of roots. The characteristic equation for this would have two duplicated roots, 3 and 3, and so we would use C1e to the 3x and then C2 with an x on it, e to the 3x. And finally, if they're complex, solve the equation. There's our complex roots. Now, in the format that I gave you and in your textbook, the 3 and the 2 are referred to by the lambda and omega. A's and B's are fine, whatever you want to call them. The idea here is to write this without complex numbers. We would write, and I'll show you that in a different PowerPoint, the C1e to the 3x, there's the 3, and cosine of 2x, there's the 2. And so each of these two independent solutions are going to have the lambda and the omega in the same place. Lambda is the exponent on the e, omega is the coefficient of x in the sine and cosine. And again, I'll show you in a different PowerPoint how that happens. And you can go see the other video on examples of all of these from the homework.